Okay, let's do a quick revision for pure physics on a chapter of electromagnetism. Okay, this is for pure physics, where we are going to use Fleming's left-hand rule. Okay, that's the main thing of this chapter. Okay, so in the previous chapter, remember we know, okay, magnetism, you put an iron core in a solenoid, okay, your iron core can be magnetized. So electricity has something to do with magnetism. So likewise, if you have a single current carrying wire like this, okay, you will have a magnetic field around it. There is a magnetic effect around it. So what is the shape of this magnetic field? Okay, you have their concentric circles. Okay, you got to draw way better than me. I remind you, and use pencil, use a compass when you're drawing this. So if there's a cross, it means that current is going in. Current is going into the paper. Okay, current is going into the paper, and a dot means current coming out. So it's concentric circles. And then obviously it is when the lines are closer, the circles are closer together, it's stronger. So as you go out, you should get weaker and your field lines should get further and further apart. Okay, so the main thing to note is, how do you know the direction of this? You don't memorize, okay, cross means clockwise and so on, don't need. You use right-hand grip rule again, okay? Here now your thumb points in the direction of the current. So if the cross, my current is going in, my thumb points inwards. It goes this way, so it's clockwise. So if there's a dot, current is coming out, my thumb points up and my four fingers point in direction of the field, so it's going this way. Alright, so that's how you get the direction of the field. Okay, so it's quite easy. Just don't get confused between right hand grip rule, because we use it here and we also use it for a solenoid. Okay, then the next thing, sometimes they ask, okay, what happens if you put a plotting compass here? Where does it point? A circle. A plotting compass consists of a compass needle made of magnet, right? So I told you, always get the direction of field. So the direction of field points this way, your compass needle point this way. So you put it here, your compass needle will point this way because the field goes this way. So you put it, let's say here, then your compass needle will point here. So the idea is always draw the field first and its direction, then you know where the compass needle points. Okay, so then we go on. Okay, for solenoid, this one you should know very well already. Alright, we did this before. Okay, if you have no core inside a solenoid, take note, it still can generate a magnetic field. Of course, this magnetic field will not be that strong. Okay, you can put a bar inside, it will be magnetized. Okay, and it will strengthen the magnetic field. Right, so the keywords which I told you was, if you put a core in there, what will you do? You'll concentrate and strengthen the magnetic field lines. Okay, and as you know, you want to make the magnetic field stronger, increase the current flow, okay, have more turns per unit length of the solenoid. Okay, all this was done in chapter of magnetism. Okay, then comes to the next part. Okay, so we know one wire has a magnetic field. So two wires, of course, they both have magnetic field. If you have two wires, one running, current running up, one running down like this, so you look from top, top means look from here down, here down, you see A. A is a dot, C is a cross. Okay, you draw their respective magnetic fields first. Okay, then you notice what? That, okay, after using your right hand grip rule, okay, for this one is going clockwise, for this one is anti-clockwise. So the inside here, these three are pointing up, all pointing up. So when you bring them close together, you can imagine here becomes much stronger. They add on to each other. So inside is stronger than the outside. So what happened? The wires will move apart. Why? Inside is stronger than outside. So the strong will push towards the weak. So you will have two forces here, pushing this wire here and pushing this wire here. Okay. Okay. The challenge is two things. One, to draw the magnetic field of these two combined together. I admit to you, I can't do it very well myself. So I have to show you in a textbook a good standard answer. It looks like this, right? You see the way they draw the field. Okay, the lines are closer, much closer on the inside, showing stronger field. And then there's hardly anything on the outside. Right, so outside is much weaker. So what happened? You push apart. So number one, know how to draw this field when they are combined together. Number two, know how to explain. So when you explain, here we go. Due to the combined effect of the two magnetic fields. Okay, in this whole chapter, this is a very key phrase. which explains almost everything. Why does the wire move? Okay, why does this turn and so on? Okay, always use this phrase. Combined effect of two magnetic fields of A and B, right, flowing to each other. They both generate magnetic field. When you combine them together, inside is stronger than the outside, so they push them apart. That's how you explain. Okay, so likewise, okay, you look through your notes yourself. Okay, what happens when you have two which are in the same direction? Same direction, they move together inwards. Why? Okay, you draw the field, you notice now, okay, again, my drawing is not great, so I show you the textbook. When they combine together, okay, this plus this, it gives you this. So we combine together, inside now you see it's weak. You see, there's hardly any lines here. There's no lines in fact. Okay, outside there are more lines. So here is stronger, push inwards towards the weaker side. Right? So that's what happens. Right? So that's why you see the book says what? Conductors or wires carrying currents in opposite direction repel, whereas in the same direction they attract. Right? That's the reason. Why? Again, okay, why does this happen? Because of the combined effect of the two magnetic fields. These two fields combined together, that's a result of it. Okay, remember this phrase, very important through the whole chapter. Okay, next. So, what happens if you have a magnet and a one current carrying wire? Individually, we can draw the fields. Combine them together, we get this. How do I get this? Look, again, this one you all know already very well. Then this one, okay, thumb points out because current is coming out, so it's going in an anti-clockwise manner. Notice left side all pointing down, strong field. Pointing down, pointing up, weaken the field. So this side gets weakened, you get fewer lines, right? Fewer lines, weak field. More lines, strong field. So how? You will push it to the right, okay? You push it to the right. So again, know how to draw this. Okay, next, how to explain, okay, when the two magnetic fields of the uniform magnetic field and that of the wire combine together again, the word combine, you can use the word interact as well. The left side is stronger than the right side, so it push it outwards, okay? So this is the key thing, right? And then, of course, you know, this I think is obvious. You want a greater force, then of course use stronger magnets, more current here. This wire pushes even more. Okay, so we know, okay, by drawing the field, everything can determine the force direction. Okay, but this takes very long time, right? So there's a faster way, okay, by using Fleming's left-hand rule. So Mr. Fleming says, okay, use his left-hand rule. Okay, left hand, not right hand. Okay, left-hand rule, where the thumb is the force, direction of motion, or what you call the force, the field. Okay, this one shows field, which is north to south, and the current. Okay, so you put your fingers this way, all right angles to each other, okay? So the way I remember, force, field, current, force, field, current, okay? So force, field, current. So we use Fleming's left-hand rule to determine the direction, okay? It is used to determine the direction. Do not say, okay, the wire moves because of Fleming's left-hand rule. No. Fleming's left-hand rule is just to tell you direction, that's all. So apply it in various situations. So for example, in this case, north to south, as I told you in class before, do the field first. Field is always easier, north to south, this finger north to south. Current, force, field, current like that? No, not right, because current is going A to B, like that my current is pointing towards me, so it should be this way. So if it's this way, then thumb points down, that means the force is pushing this down. So this whole wire moves downwards. Okay, because of what? Again, read for yourself. Keywords, everything. That causes a force to push it down. And I use Fleming's left-hand rule, I determine the direction. Okay, then the next page was more practice. 2, 3, 4. Okay, you all know how to do. Then come to 5A, you notice something. This one you can't apply Fleming's left-hand rule. You cannot put your Fleming's left-hand rule like this. Okay, no such meaning, alright? So, in these two cases, there is no force exerted. There is no force exerted on wires when the direction of the magnetic field is parallel to the direction of current, right? Whether the current running this way or this way is parallel to the direction of field, there's no force. So these two have no force exerted on it at all, okay, compared to the others. So from there, one single wire, you bend the wires this way into a coil, right? When you bend into the coil, okay, you apply Fleming's left-hand rule 2 times, one at AB, one at CD. Of course, before that, you must know the direction of current. At BC, you don't have to apply. Why? Because there is the current is running parallel to the field, so you don't have to apply Fleming's left-hand rule here, okay? And then, of course, know the reason why there's a force here, why there's a force here, causes this to spin, right? And then, of course, 4 ways of making this spin faster, stronger magnets. Do the easiest first. Increase current flow in the coil. Put a core inside the coil such that it strengthens and concentrates the magnetic field. Okay, and then have more turns around the core. Okay, all that will help. All right. Then for MCQ, sometimes they ask you this. Okay, what happened now? In these crosses, this magnetic field going in. So all these are going in. So when your current is coming here, you apply your Fleming's left-hand rule, you find the current is diverted this way. Okay, and be careful with MCQ when they say electron beam. Okay, when you use Fleming's left-hand rule, the force field current direction will be opposite electron beam. Okay, because when we use Fleming's left-hand rule, the current follows conventional flow current, so it should be the opposite. Okay, so you have to put the fingers in the opposite way. Okay, maybe I just show you. Let's revise. Okay, magnetic field is coming out. Force, field, okay, my field coming out, right, field coming out, okay, then what happens? My current is going this way. Why? Opposite electron beam, so thumb pointing down, that means the force is pushing this electron beam down, okay, so like that, okay, so you need to adjust your hand a little bit and do it correctly, okay, so take note of this. Right, so actually the main concepts of all these applications, the main big application is the DC motor. Okay, the DC motor, how does it work? Okay, you want to see how it works, you can always look at YouTube, Google, you can find videos on it. Okay, and then how do you explain? Okay, read through your notes, all this. This is a shortened version actually, right? Okay, first, of course, always trace the flow of the current, right? And then after that, apply Fleming's left-hand rule here and here. Then after that, you know how it spins. So this is first step, okay, at 0 degrees. Okay, then after it will start to turn. Okay, you go and read through yourself. Okay, and also, oh yeah, I forgot to say, know how to draw a simplified diagram. A simplified diagram can be simple. The main focus is here. In fact, here is not so well drawn. Here, you should draw the wires connected. So my simplified diagram will look like that. Okay, something like that, something simple like that. Okay. Okay, so it looks like this. So the carbon brush, commutator, okay, split ring commutator, okay, they are not joined together, it's a ring, half a ring, okay. Then this goes to the outside, to your battery, your switch, okay, the rheostat not that important, and then your magnet. So this is the way you draw a simplified diagram. If you can't draw that, okay, never mind, at least you can draw something simple. But of course, label everything after you drew. What is this, and so on. Okay, so then after that, be able to explain, okay, what happens when in this position. Then it spins to a vertical position. Okay, momentum brings it to over to the other side, and then what happens? You will have again force acting on a coil, okay, and it will continue to rotate in one direction. Why? Because the split ring helps to reverse the direction of current in the coil after every half revolution. Okay, so it keeps on turning in one way. Right, so go and read through this yourself. Okay, I've done this very briefly. And then after that, sometimes they do also ask you the function. What's the function of split ring? What's the function of carbon brush? So again, go and make sure that you study this. Okay, after they can easily ask you, okay, after describing, okay, what the function, then at least you know. And also application, like toy fan, motor or toy car, electric drill, hair dryer, and so on. That's where you can find it. Alright, okay, let's just look at applications for very examples. Okay, so when you see a situation like this, okay, you know that this electromagnetism. So why does the rod move? Okay, so it's always good to say close the switch, and then when the current flows through the aluminium rod, okay, track the flow, the current goes this way. Okay, when current flows through the aluminum rod, what happens? You will set up magnetic field around the aluminum rod, and this magnetic field combined with the magnetic field of the magnet results in a force acting on the rod. Okay, so that's how you explain. And then to determine direction of the force, you use Fleming's left hand rule. So you use Fleming's left hand rule, force, field pointing down, current this way, right? Coming this way. Okay, already got to bend my fingers in a weird way. Thumb pointing in, so the rod moves inwards. Okay, so explain properly, step by step. Okay, in this manner, right? So for this question, then again, if you look further, turn down to this question, very similar. Okay, it may look a bit different, but it's a similar thing, same thing. Close the switch, look at the way the current flows. Where is the current flowing? Okay, which direction is the current flowing? Here I actually never even show the positive negative. Okay, right? So you see for yourself, okay, this moves this way, they did show the current is coming this way. That means here is positive, here is negative, right? So current going this way, right? So when current goes this way down, okay, this magnetic field is set up around this coil, okay, or wire, and it combines with the magnetic field of this magnet, resulting in a force pushing it up. So force pushing this way. So you apply the Fleming's left hand rule, you must be able to show that he's pushing it this way. Okay, so that's how you explain step by step. Remember keywords, key phrases. And then how they explain the direction of the force. So explain direction of force, simply say by using Fleming's left hand rule. Don't stop there. Say what does Fleming's left hand rule represent? What does the thumb represent? The forefinger, okay, second finger, what do they represent? Force, the field, and the current. Okay, so explain what they represent. Okay, so it should be quite okay. So the rest of the application, okay, you can go and try it out for yourself. It should not be too difficult. So there is a very quick 17.5-minute revision on this chapter, right? So then I leave you to go and practice the other questions for yourself. That's it.